Section: Introduction. In this section, we explore the final training stage of modern language models, LMs, known as learning from preference feedback. This training phase has been beneficial for models like ChatGPT, Llama 3, and Claude, enhancing their performance in various tasks such as instruction following, coding, math, and summarization. However, the methods used for preference-based learning differ widely, making it unclear which aspects are most crucial for model performance. Specifically, we focus on two popular algorithms, PPO and DPO, which approach preference-based learning differently. Both DPO and PPO rely on preference data for training, with DPO directly training the model and PPO training a reward model first. The reward model in PPO is then used to evaluate the generations from the main model based on a set of training prompts. We aim to investigate the key components of learning from preferences systematically, starting from a strong initial model and examining the impact of each component on model performance. Our study reveals that the quality of preferences, the choice of learning algorithm, PPO versus DPO, and the size of the reward model and training dataset all play significant roles in model performance. We find that using synthetic diverse data with per-aspect preferences yields the best results for preference-based learning. Additionally, we observe that PPO generally outperforms DPO across various datasets. Increasing the size of the reward model and training dataset improves the reward model's performance but has limited impact on overall model performance. Furthermore, using tailored prompts during policy training can enhance model performance in specific domains, such as math, but shows minimal effect on overall performance. Overall, we recommend using synthetic preference datasets and training with PPO using a large reward model for optimal performance. Tailored prompts are suggested for specific tasks of interest. Moving on to the comparison between PPO and DPO, DPO is more computationally efficient and does not require training a separate reward model. However, PPO, which trains on online data, tends to outperform DPO in various scenarios. Our evaluation covers a wide range of datasets and considerations, providing insights into the performance of models trained with PPO and DPO. We base our experiments on the Tulu 213B model, exploring alternative datasets, training algorithms, reward models, and policy training prompts to enhance the performance of the Tulu 2 models. Our evaluation includes 11 different benchmarks assessing skills like factuality, reasoning, truthfulness, coding, safety, and instruction following. By examining these aspects, we aim to push the performance boundaries of the Tulu 2 models. Section Summary. In this section, we explore the importance of learning from preference feedback in modern language models like ChatGPT, Llama 3, and Claude, focusing on the two popular preference-based learning algorithms, PPO and DPO. We find that using synthetic preference datasets and training with PPO, along with a large reward model, yields the best overall performance, especially when targeting specific downstream tasks. Additionally, the quality of preferences and the choice of learning algorithm play crucial roles in enhancing model performance across various evaluations and datasets. Section: Exploring learning from preference feedback. In this section, we delve into each aspect of learning from preferences, preference data, learning algorithm, reward models, and policy training prompts. When it comes to preference data, we compare how models trained with DPO perform across 14 different datasets that include human annotation, web scraping, and synthetic generation. We find that synthetic data with per-aspect annotations tends to perform the best, outperforming human annotated and web-scraped datasets, especially in truthfulness. Datasets that gather per-aspect annotations and then average across these scores show better performance compared to datasets that rely only on overall judgments. For instance, help steer and ultra-feedback datasets perform strongly even when smaller in size compared to other datasets. Moving on to the preference learning algorithm comparison between DPO and PPO, we find that PPO enhances reasoning, coding, and safety capabilities more than DPO. Models trained with PPO show improved chain of thought reasoning abilities, even without specific examples. Additionally, PPO-trained models tend to excel in certain evaluations like Alpaca Eval compared to DPO-trained models. When studying reward models, we explore ways to enhance them, such as scaling up training data and increasing model size. Surprisingly, we observe that improvements in reward models do not always lead to significant enhancements in overall downstream performance during PPO training. Despite using larger reward models, the improvements in performance are marginal, indicating the complexity of translating reward model enhancements to policy improvements. It is crucial to evaluate over a diverse set of tasks to understand the impact of reward model size and training on overall performance accurately. Section Summary. In this section, we explore learning from preference feedback by comparing models trained with DPO across various datasets, where synthetic data with per-aspect annotations outperforms human annotated and web-scraped datasets. When comparing learning algorithms, PPO shows improvements in reasoning, coding, and safety capabilities over DPO, with models trained with PPO demonstrating better chain-of-thought reasoning abilities. Additionally, we investigate reward models and find that scaling up the reward model size does not necessarily lead to significant improvements in downstream performance during PPO training, highlighting the complexity of translating reward model enhancements to policy improvements. Section: Policy Training Prompts. In this section, we explore the impact of using different types of prompts for training policies. We start by focusing on improving specific skills, such as math performance evaluated by GSM, and then move on to enhancing overall performance. This differs from previous studies that either reuse prompts from reward model training or use a generic set of expected user queries. When we target specific prompts for training, particularly for math skills evaluated by GSM, we create 3 sets of prompts: those from the GSM training set, math-related prompts from various datasets, and 20,000 random prompts from Ultra Feedback. We explain how we identify math-related prompts in more detail in the appendix. We then use these prompts to train models with PPO and each reward model from the previous section. Our results show that larger reward models perform better when the training prompts closely match the test settings. For instance, using prompts from the GSM train set with 70 billion reward models leads to significant improvements in GSM performance. On the other hand, weaker reward models struggle when faced with prompts that differ from their training set. Interestingly, training with the 13 billion Ultra Feedback reward model performs worse when using prompts other than those from Ultra Feedback. This could be because the reward model does not generalize well to unseen prompts. Similarly, the 13 billion mix and 70 billion Ultra Feedback reward models find it challenging to utilize math prompts, which are out of domain for the reward models but in domain for the task. Overall, these findings suggest that targeted prompt distributions can enhance performance, especially when combined with powerful reward models, like using prompts from the GSM train set and evaluating on GSM. Building on the success of targeted prompts, we create a new set of prompts by selecting 20,000 math and 20,000 code-related prompts using a similar method as before. We then merge these prompts with Ultra Feedback prompts to form a larger prompt pool, which we randomly downsample to 60,908 prompts. This rebalances the prompt pool to focus more on coding and math tasks, with the aim of improving performance in these areas while maintaining overall performance. However, our results show that using mixed prompts does not necessarily enhance performance in a general setting. Specifically, when looking at math and code results, we do not consistently see improvements with the altered prompt mixture, and overall performance tends to decrease. This could be because Ultra Feedback is already diverse, allowing us to achieve strong performance in math and coding evaluations when considering the entire dataset. Shifting the prompt distribution away from other tasks slightly impacts overall performance negatively.